Hello and welcome to The Sleepy Scientist, where curiosity gets cozy and science takes the scenic route to sleep. Tonight's gentle exploration centers on one of the most puzzling yet constant elements of our lives: time. It slips quietly through our hands, shapes our routines, and occasionally plays tricks on us, especially when we're waiting for a kettle to boil before we begin unraveling the ticking fabric of time. I'd love to know, where in the world are you watching from, and what time is it for you right now? Fitting, isn't it? A video about time, and yet here we all are, gathered across different time zones, each experiencing this moment in our own slice of the clock. If you find this journey relaxing, thought-provoking, or simply a gentle way to wind down after your day, I'd truly appreciate it if you gave the video a like or considered subscribing. It helps this quiet corner of curiosity find others who might enjoy a peaceful pause, too. I hope this isn't so interesting that it keeps you awake, but if it does, at least you'll drift off having learned something about the nature of the universe. So, get comfortable, clear your thoughts, and let's begin. Because somewhere between fleeting seconds and vast centuries, between dreams and daylight, lies the story of time. Time has a curious way of stretching and shrinking. 10 minutes stuck in traffic can feel endless, while 10 minutes spent on something you love passes in a flash. And yet, clocks tick on steadily, second by second, minute by minute. So what's happening? The answer starts not with physics, but with the brain. Our sense of time, our awareness of when things begin and end, is surprisingly flexible. Psychologists call this subjective time, and it's strongly influenced by attention, emotion, and memory. In other words, your experience of time might differ significantly from how time actually passes. Let's begin with something familiar: waiting. Picture yourself in a waiting room. The decor is dull, the magazines are outdated, and the clock ticks loudly in the background. 5 minutes can feel like 30. That's because your brain lacks stimulation, and your attention turns inward, making each passing moment feel longer. Now think about a lively chat with a friend or getting lost in a book. You're fully engaged and your brain stops closely tracking time. It's as if your mind says, "We're busy. No need to monitor the clock. Time flies." This mental state is known as flow, a term coined by psychologist Mihaly Csikszentmihalyi, where you become completely immersed in the present. Novelty also affects time perception. When you experience something new, your brain takes more time to process and store it. Later, it feels like more time passed because your memory holds more detail. That's why childhood summers felt endless. Your brain was constantly logging new information. As routines settle in with age, the brain compresses memories. Fewer highlights make time feel faster. Emotion influences time too. Research shows that fear and anxiety can make time seem slower, while joy and excitement make it fly. In high-stress moments like a near accident, the brain forms dense memories, creating the illusion that time slows down. It's not that time actually slows. It's that the brain captures more detail per second, like a mental slow-motion replay. Then there's boredom. You've heard, time flies when you're having fun, but the reverse is just as true. When bored, the brain's internal clock, yes, that's a real term, becomes more active, producing more mental pulses. This makes time appear to drag. It's like having an overly eager drummer in your head marking every beat of a dull moment. Culture and language shape our time perception, too. In English, we treat time like a resource. We spend it, save it, or run out of it. Some languages, like Hopi, conceptualize time differently, not as a line, but as a set of states or experiences. In some cultures, people point behind them, too. Indicate the future because it's unseen, and ahead to indicate the past because it's already known. A complete reversal of what many of us are used to. What about internal timekeeping? Surely our bodies must have some built-in mechanism to track time, and we do to an extent. Humans follow a circadian rhythm, a 24-hour cycle regulating sleep, body temperature, and hormones. But that's more like a daily alarm than a stopwatch. For shorter interval seconds and minutes, scientists believe we rely on a mental timekeeper, often compared to an internal stopwatch. This involves brain areas like the basal ganglia and cerebellum, which rely on neural pulses. When estimating how long something lasts, we subconsciously count these pulses. However, we're not always accurate, especially when multitasking, distracted, or emotional. There's even a phenomenon called the return trip effect, where the journey back feels shorter than the journey out, even though both take the same time. Why? On the way out, your brain processes new surroundings. On the way back, it already knows the route, making it feel quicker. And of course, there's the universal time distortion, the snooze button. Somehow, those 9 minutes between alarms feel shorter than any other 9 minutes. While there's no firm science yet, it likely involves interrupted sleep, partial consciousness, and a confused internal clock. So what is time, at least from our perspective? It's not just a number on a watch or the shadow on a sundial. It's a sensation, a perception shaped by memory and focus. It bends with emotion, age, and even the language we speak. It races when we're in love, slows when we're scared, and sometimes vanishes completely. Even as physics aims to explain time on a cosmic scale, our lived experience of it will always be deeply human, fluid, fascinating, and sometimes wonderfully unreliable. If time is strange, our efforts to measure it reveal our creativity and our impatience. From ancient tools to atomic clocks, we've spent millennia trying to pin down an invisible force. Just to organize our lives around it, let's go back to the beginning, when the first timekeepers weren't machines, but the sky itself. Early humans were keen observers of the heavens. Sunrise, sunset, moon phases, and seasonal changes were nature's clocks. Around 1500 BCE, the ancient Egyptians built towering obelisks as sundials. By observing the shifting shadows, they divided daylight into segments. Though these hours varied with the seasons, it was accurate enough for farming, rituals, and daily life. Next came water clocks used by Egyptians, Greeks, and Chinese, which measured time by the flow of water from one vessel to another. They worked even at night, unlike sundials. Some were elaborate, featuring gears and chimes. Ancient smart devices, just a bit soggy. Meanwhile, in Mesoamerica, the Maya developed intricate calendars that tracked solar and lunar cycles with remarkable precision. Their long count calendar measured thousands of years, an impressive feat for a civilization without metal tools or beasts of burden. In Europe, mechanical clocks didn't appear until the Middle Ages. Early versions were large and installed in churches and monasteries. They didn't have faces or hands, they just rang bells at regular intervals to remind monks to pray. In a way, monks were the original alarm clock users, much more calmly than most of us. A major breakthrough came in the 14th century with the Verge escapement, which allowed for more controlled energy release. This led to smaller, more accurate clocks, eventually featuring dials and hands so people could see the time. Not just hear it. In the 17th century, the pendulum clock emerged thanks to Dutch scientist Christian Huygens. Accurate to within a minute a day, it vastly outperformed earlier designs. If time were a horse, the pendulum was the saddle that made the ride smoother. More precise timekeeping became vital during the age of exploration. Navigators needed to know their longitude, which required knowing the exact time at a reference point. Enter John Harrison, an English carpenter who invented marine chronometers, highly accurate, sear-resistant clocks. His fourth model, the H4, transformed navigation and earned him long overdue recognition. By the 20th century, quartz technology revolutionized timekeeping. Quartz crystals, when charged with electricity, vibrate at a highly stable frequency. These vibrations allowed for precise, affordable clocks and watches, making punctual trains and appointments more realistic. But for ultimate precision, we turn to atomic clocks. First developed in the 1950s, they measure time using the vibrations of atoms, usually cesium or rubidium. A cesium atom, for example, oscillates exactly 9,192,631,770 times per second. That number defines the second in the international system of units. Atomic clocks are so accurate, they'd be off by less than a second after 100 million years. Today, they're used to synchronized GPS systems, internet servers, communication networks, and global finance. Without them, your maps wouldn't work, transactions would falter, and meetings would unravel. Time, once measured by dripping water and shifting shadows, is now marked by atomic vibrations in shielded labs. And still, it remains deeply personal. We may slice it into neat units, but we all live it differently. So why did we start measuring it at all? Perhaps to guide prayers, plant crops, or schedule trade. Or maybe because, for all our wonder at the cosmos, we're comforted by rhythm. The steady beat of time, however elusive, shapes our lives. A tick, a talk, a quiet whisper reminding. U.S., you're here now. For most of history, time was a local matter, rising with the sun, pausing at dusk, and flowing with the rhythm of bells or bird calls. Then came Isaac Newton, a man determined to describe, define, and organize the universe. Newton, the 17th century English physicist known for both his contributions to science and that infamous apple, gave the world a model of time that would shape thinking for centuries. In his view, space and time formed a fixed stage on which the universe played out. Objects, planets, apples, cannonballs, and bicycles moved across it, but the stage itself never changed. Time, in Newton's universe, was absolute. It ticked forward at a constant pace for everyone, everywhere. As Newton put it, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. In other words, time was like a river flowing steadily whether anyone noticed or not. This idea made intuitive sense. Drop an object today or tomorrow, here or elsewhere, and Newton's equations could predict where it would land as long as you understood the math. Time became a stable backdrop for understanding motion and force. This model allowed scientists to calculate planetary orbits, pendulum swings, and cannonball paths with impressive accuracy. Time, in this framework, was impartial, uniform, and unchanging, but this view made one key assumption: that time existed independently, like an invisible beat guiding the universe. Some thinkers weren't convinced. Among them was Gottfried Wilhelm Leibniz, Newton's intellectual rival and co-creator of calculus. Leibniz didn't agree with the concept of absolute time, or Newton's version of calculus for that matter. He argued that time wasn't some universal background, but rather a way to describe the sequence of events. In his view, without events, time doesn't exist. It's not an independent entity, but a relationship between occurrences. Imagine a clock ticking in a completely empty universe, silent and dark. Newton would say it's still measuring time. But to Leibniz, it's just an ornament, doing nothing of significance since there's nothing to measure. For him, time only has meaning when things are actually happening. Newton strongly disagreed. He maintained that time is real and flows uniformly, regardless of what's taking place, which, to be fair, does align with the feeling of waiting. For water to boil, Newton's view later became the backbone of what we now call classical mechanics. And for a long time, that framework worked remarkably well. It described the movement of falling objects, swinging pendulums, planetary orbits, even the complicated motion of a juggling unicyclist. So it's worth recognizing how successful Newton's model was. For centuries, scientists used his concepts of absolute time and space to make sense of the natural world. As clocks became more accurate, navigation improved. Engineering advanced. Trains ran on schedule, or at least had a better excuse when they didn't. But here's the catch: despite its strengths, Newton's system began to falter under closer examination. In the 19th century, scientists studying light and electromagnetism started noticing oddities. Experiments showed that the speed of light stayed constant, no matter how fast the observer was moving. That didn't fit Newton's model. If you're in a car moving quickly, you'd expect to gain on light a little faster. But you don't. Light still travels away at the same speed. This puzzle lingered until a young patent clerk named Albert Einstein entered the scene. But we'll save that part for another section. For now, it's enough to say that Einstein politely acknowledged Newton's model and then completely overturned it. Still, Newton's idea of a universally flowing time left a strong mark on science and daily life. We often talk about time as something we can waste, spend, or safe phrases that assume time behaves like a resource that steadily moves forward. Work schedules, school bells, and microwave timers all rely on the belief that time ticks the same way for everyone. And in most day-to-day situations, that idea holds up. Whether you're baking, commuting, or waiting for a delivery, Newton's time works just fine. It's only when we get into areas involving very high speeds, intense gravity, or subatomic scales that Newton's version starts to lose precision. So, in the broader story of time, Newton gave us a strong middle chapter, a picture of a mechanical, predictable universe operating like clockwork. He brought structure to the cosmos and helped us make time something measurable and understandable. But as we'll see, time has more than one character. While Newton's version is clean and logical, the universe may be more complex. If Newton imagined time as a steady, endless river flowing the same for everyone, then Einstein came along and said, actually, it's more like a flexible, shifting trampoline. That's not an exact quote, but it's surprisingly close. In the early 1900s, Einstein radically changed how we understand time with a theory that redefined the structure of reality. He called it relativity, and it came in two parts: special relativity and later general relativity. Both had deep implications for time and neither matched our everyday experience. Let's start with special relativity, which Einstein introduced in 1905 at the age of 26. While working at the Swiss Patent Office, possibly spending his lunch breaks rethinking the universe, a core idea of special relativity is that the laws of physics, including the speed of light, are the same for all observers, regardless of how fast they're moving. This challenges Newton's absolute time. In Newton's view, even if two people are moving at different speeds, they would still agree on the order and timing of events. But in Einstein's framework, that's not always the case. What looks like simultaneous events to one person might appear differently to someone else moving at a different speed. This leads to one of special relativity's most surprising results: time dilation. Simply put, the faster you move, the slower time passes for you. Compared to someone who's standing still, if you were to travel on a spacecraft moving close to the speed of light, your onboard clock would tick more slowly than a clock back on Earth. On Earth, time passes a bit more slowly for you. Your hair would grow slightly slower. You might even miss a few seasons of your favorite show. And no, this isn't science fiction, it's a measured effect, a well-known experiment demonstrated this using atomic clocks flown around the world on planes. When compared to identical clocks that remained on the ground, the ones in flight ticked just a tiny bit slower. It wasn't a huge difference, nothing you'd notice unless you were obsessively punctual, but it proved a real point. Time slows down with speed. Then there's the famous twin paradox. Imagine identical twins. One sets off on a high-speed journey across the galaxy while the other stays home, feeds the cat, and waits. When the traveling twin returns, they're younger than their sibling. Not because of better space skincare, but because their time genuinely passed more slowly. This isn't a contradiction. It's a strange but valid result of Einstein's theory of relativity. It sounds strange, but it's well supported. Speed, however, isn't the only thing that distorts time. In 1915, Einstein expanded his ideas into the broader theory of general relativity, which included gravity. In this theory, gravity isn't seen as a force, but as the bending of space and time caused by mass. A more massive object bends the space. Around it, imagine a heavy bowling ball placed on a soft mattress. If time were painted onto that mattress, it would stretch and warp along with the surface. So, the closer you are to a massive object, the slower time moves for you. Stand near a black hole or even just next to your friend's overpacked suitcase and time ticks a little slower than for someone farther away. Again, this isn't just an idea. It's been confirmed through measurement. One experiment placed atomic clocks at different altitudes, one at the base of a mountain and the other at the top. The lower clock, being closer to Earth's center of gravity, ticked ever so slightly slower. Even a difference of a few centimeters in height can produce a measurable effect. That means, yes, technically, your head is aging just a bit faster than your feet. This effect, known as gravitational time dilation, has practical applications. 2. GPS satellites orbit Earth at high speeds and greater altitudes. Their motion slows their clocks while their distance from Earth's gravity speeds them up. To maintain accuracy, their onboard clocks are continually adjusted to balance these distortions. Without those corrections, your phone's location could be off by kilometers in just minutes. Time doesn't flow in a straight line. It bends and flexes, and modern technology must account for that. So, what does all of this mean for our understanding of time? Einstein showed that time isn't a fixed universal backdrop. It's more like a flexible fabric closely tied to space. It can stretch, twist, and shift depending on motion and gravity. That means your experience of time depends on where you are and how fast you're moving. It's a strange thought, but also kind of elegant. Time isn't the same for everyone. It's relative personal. Even like your favorite kind of tea, Einstein's ideas didn't just change physics, they reshaped how we see the world. Time isn't a constant ticking in the background. It moves with us, shaped by the matter and energy all around. Even if we don't feel these shifts in everyday life, every moment we experience is subtly shaped by them. So next time someone says they're running out of time, you might gently point out that time passes differently depending on speed and gravity. Then pause, smile, and maybe step back. Now, imagine for a moment that everything around you started to run backward. Toast jumps from your mouth onto the plate, already buttered. Your tea heats up as you drink it. Raindrops rise into the sky. It would certainly feel odd. But is it impossible under the laws of physics? Not really. This strange scenario touches on one of the most puzzling ideas in science. Why does time seem to move in only one direction? Many core physical laws like Newton's equations or quantum mechanics don't care about direction. They work the same whether time moves forward or backward. If you filmed two particles colliding and played the footage in reverse, the equations would still work. No red flags would be raised. And yet, in our daily lives, time feels like a one-way path. Eggs break but don't unbreak. Paper burns but ashes don't turn back into pages. We remember the past but never the future. So what causes this disconnect? Why does time, at our everyday scale, move so steadily from yesterday toward tomorrow? This is where the concept of the arrow of time comes in. The arrow of time is a way to describe how time seems to flow in just one direction from the past into the future. And the key to understanding it lies in one of physics' most essential and sometimes messy principles, the second law of thermodynamics. This law tells us that in any closed system, like the universe, entropy tends to increase over time. Entropy is a way to measure disorder or randomness. In simpler terms, the things naturally move from organized to disorganized. You can scramble an egg, but you can't unscramble it. Your desk will slowly become messy unless you clean it. And socks seem to vanish but never come back in pairs. This universal trend toward greater entropy is what gives time its direction. It's why we experience events in a sequence from a more ordered past to a more disordered future. There's no going backward unless you're a time traveler or a fictional wizard with a very specific spell. Here's another way to picture it. Imagine dropping a glass and it shatters on the floor. Now the glass is in a high entropy state, scattered and disorganized. The odds of all those shards reassembling themselves into a perfect glass? Not zero, but so unlikely that it's practically impossible. Physics allows for time to run backward in theory, but in practice, probability doesn't cooperate. And this brings us to one of cosmology's most puzzling questions. Why was the universe so low in entropy at the beginning? If entropy increases, then there must have been a starting point, a kind of cosmic clean slate from which all this disorder began. The leading explanation is that, just after the Big Bang, the universe was incredibly uniform, smooth, balanced, and highly ordered. As time passed, gravity and cosmic expansion disrupted that balance. Galaxies formed, stars exploded, and socks vanished faster than ever. But why it began in such an orderly state? That's still one of science's great unanswered questions. Some researchers believe the answer lies in how entropy, time, and the very shape of space are connected. Others wonder if we're even asking the right question, like a goldfish trying to understand the water it swims in, interestingly. There are other arrows of time, too, and they all point in the same direction. There's the psychological arrow. We remember the past, not the future. That's because memory depends on physical processes in the brain processes that leave behind traces, and those traces reflect entropy increasing. You can't remember the future because it hasn't happened. There are no traces yet. There's also the causal arrow. Causes come before effects. You flip a switch and the light turns on. You don't see the light first and then decide to flip the switch. Again, this follows entropy. Adding energy, like turning on a light, spreads it out and increases disorder. Finally, there's the cosmological arrow, the ongoing expansion of the universe. Galaxies drift farther apart. Space stretches. The cosmos continues to cool. And all of this gives time a distinct direction forward.